for the intro, Matt, and thanks for the invitation as well. Can you hear me all well?
Yeah, perfect.
Good, lovely. So yeah, as Matt said, I work at the University of Lincoln. I'm a senior lecturer here, leading the MA program. And my interest, if you like, on analogical reasoning dates back to my postgraduate studies, which, you know, it feels like a long distant memory, but yeah. So part of the seminar today will be more about, if you like, the implications of the research we've been doing on the use of analysis in science teaching, more than the research, if you like, in itself, which you can read more about in our publications in that topic. The title is From the Didactic to the Heuristic Use of Analogies in Science Teaching. There's two areas of main focus for the seminar. One has to do with how we can use analogies, if you like, for didactic purposes, and that refers actually to other analogies that teachers generate themselves, or actually choose to use, if you like, as part of the teaching process. And those actually that the students generate. And then the second, if you like, part will be more, if you like, what I would say is something that research has not paid attention to, and that refers to how such a use of student-generated analogies can be used productively, if you like, in the teaching of science. So I have that comic script here. I'm not sure if you can read that through. There is a distinction made, if you like, in the literature concerning the different types of similarities we draw, and whether we're talking about similarities in the properties of the objects, their attributes, the relationships, etc. And of course, if you like, all these differences have been reflected on the use of different terms for the descriptions of the comparisons we make between a familiar and an unfamiliar, if you like, situation, phenomenon, object, and so on. Mainly, perhaps, you know, that's my kind of like of argument around the main terms used around the sort of similarities. Therefore, and there's no clear distinction among these, if you like, among the three terms that are of an analogy, or at least, if you like, the difference in most cases is not very explicitly made. The terms used include metaphors that Benny spoke about, similes, examples, and in some cases even models. But I would argue that that all of the different terms, if you like, coexist with an analogy, or perhaps that they're all, if you like, close relatives to an analogy. And I've seen, if you like, in the literature, the terms being used, if you like, interchangeably. Now, some of the examples I will be providing, if you like, as part of the seminar, they may be more akin, if you like, to examples or even models, but I will be referring to them as analogies. As I think whether something is an analogy, a simile, a model, if you like, a metaphor, seems to be, at least if you like, for the purposes of our research, less relevant than the analogical reasoning as a process that essentially, you know, someone employs in an attempt to perceive and explain the unknown, the unfamiliar, the new, if you like. So here, the two, if you like, main components of an analogy that I'm sure you're all familiar with, and perhaps you know, I should thank again for the opportunity to present our work in an experienced, if you like, audience in this area, with no need to expand further on definitions, components, function of analogies, etc. Perhaps I should say here that much of the seminar would not be, if you like, on the mechanisms behind, you know, analogies, how they function, if you like, the transformation of the one situation to approach the new, if you like, and so on. But, you know, just to put, if you like, into context and define what I mean by analogy. An analogy, if you like, is nothing more, and that's how it will be used in the seminar, than relations between two, or perhaps, if you like, more things that I compare. And I have, if you like, two components. Oops, sorry. The known situation, which forms the basis to approach a target situation, which again, the target situation is nothing more than the unfamiliar situation. And this can be an unknown idea, a novel situation, an unknown concept, a new phenomenon, anything, which of course is under examination or if you like, for which knowledge and understanding is desired. So just, if you like, here a schematic representation, and it's funny when you're talking about representation analysis and you give, if you like, such a schematic representation. So that's a schematic representation of the function of an analogy with aspects of the base situation transferred or compared to, if you like, to the target situation in that analogical relation, without, however, that excluding transfers from the target back to the base in that process of approaching the new and unfamiliar. Now, historically, analogical reasoning has played arguably an important role in a wide range of problem-solving contexts. It has also been proven a useful, if you like, a useful device in teaching and learning. Now, in research and science teaching, science education, there's been a lot of studies that have shown the effectiveness, if you like, of analogies as a didactic tool, which, well, where appropriately and effectively used, facilitates the learning process of newly introduced concepts, newly taught, if you like, concepts, abstract concepts, new phenomena, new situation. Now, this is because analogies allows the use of what is known and familiar in order to understand what is new and unfamiliar. Or in other words, it is usually, if you like, through the use of analogy that teachers, if you like, educators more generally speaking, help the students build knowledge upon prior understandings, observations, upon their experiences, with such a learning fitting in with what has been termed, if you like, as a constructivist approach to learning, essentially being taught or learned from what we know or what we observe, etc. Now, the vast, if you like, majority of the studies in science education have focused on the use of analogies in that, if you like, exact way, as a teaching tool, as a didactic tool, in which, you know, the teachers provide the analogies to the students. Sometimes they do generate the analogy, or they choose, if you like, their analysis because they consider them to be appropriate, if you like, for that concept they're about to teach. And they use, if you like, these, if you like, well, the students are being asked to use these analogies in order to understand, if you like, and develop the knowledge for that newly taught concept, or as I said before, an unfamiliar phenomenon. And that's what I'm referring to here as a didactic use of teacher-generated analogies. The didactic use of analogies, and I'm talking about those generated by teachers or chosen by teachers, with the aim of facilitating the understanding of the new concept, as I said, has been described in the literature as a double-edged sword, in that if not used with caution, it can lead to undesired outcomes, contrary perhaps to the intended ones, contrary to the function of analogies in facilitating that understanding. And we shall look at some examples like why that actually may happen. So here is a rather, I would say, widely used, well-known example of such an analogy. It's been used widely in physics and chemistry teaching. So this is the solar system provided as an analogy for the planetary model of the atomic structure. And of course, that refers to similarities in orbits between planets around the sun in the solar system and electrons around the nucleus in the atomic, if you like, structure. Now, in this sense, the analogy is a detailed, if you like, comparison that works by drawing similarities of the relative motions of objects in both the base and the target situation. Now, that's, if you like, similarity can be used as a basis to infer further additional similarity. It can be extended, if you like, to other aspects of the base target system, like the centripetal attractive force in both the base and the target. That, of course, is responsible for that motion, if you like, around the sun in one case and around the nucleus in the other. Now, the use of that analogy from the teacher's supply presupposes that the student hold a very good understanding of the base situation, the solar system. And they know of those elements, if you like, that are to be mapped, that are to be related from the base to the target. Like I said, the centripetal attractive force, responsible for the planet's motion around the sun in the solar system, and the electrons around the atom nucleus in the other. Now, if it's not the case, and students do not have such a knowledge of the base situation, then the analogy won't function, and it won't serve as a didactic tool here in helping the students understanding the atomic structure. So part of that double-edged sword nature of such analogies, it's the possible, if you like, absence of knowledge of the base domain, or perhaps an underdeveloped, if you like, knowledge of it. Here's another example of another, if you like, analogy, and we'll see, if you like, why that's another double-edged, if you like, sword. But that analogy is the water being compared, if you like, to electricity, in that they both, if you like, flow, both the water and the current flow. It's based, if you like, on the familiarity that most students, I would say, will have with the idea of water flowing through a pipe, which can indeed make it suitable analogy for current flowing through the wires of an electrical circuit. For instance, as you will see here in the picture, the students can use the flowing water analogy to understand current flow in simple circuits in which the flow of water through the wide and narrow pipe can be compared to the flow of current through a thick and a thin wire. However, having setting up these analogy, there's a potential to introduce some confusion for students, in that while we use the word, if you like, closing with respect to the electrical switch, when actually we mean turning current on, when we say closing the tap in the water system, it actually stops the flow of water. So it's perhaps important for teachers that they don't only recognize the value of this analogy or analogies like this, but they also recognize that those same analogies can inadvertently lead to unexpected confusion. Now, another issue perhaps with this analogy is that, and most, I would say, analogies, that the teachers should make very explicit where the analogy breaks down, as without actually the limitation of the analogies being made explicit, and in this particular case, there's no reason for the student not to implicitly assume that as a break in the hose pipe results in the leakage of water, so a crack in a wire results in the leakage of electricity, which isn't the case. So, so just to recap, what may be problematic in the didactic use of teacher-generated analogies is that they can also elicit alternative conceptions or misconceptions, they're more widely named. This is because students can view the analogy differently than the teacher, and thus draw different relationships and similarities between the base and the target. After all, I mean, because the teacher generates those analogies, the base situation are drawn from their own knowledge repertoire, their conceptions, their beliefs. With regards to the didactic use of analogies, they have another potentiality, which could also contribute to the facilitation of students' learning of science when used, if you like, as a teaching tool. We have found in our research, among research of others, actually, that each individual's prior knowledge influences the understanding of a new phenomenon or a problem, an unknown situation, if you like. As well as it influences, if you like, the generation of analogy the individual uses to approach that unknown situation. Now, in turn, this knowledge can be reflected in the analogies generated. So the argument here is, if you like, in terms of the use of analogies in the teaching process, is that they can reveal, if you like, students' intuitive knowledge, which form the basis for their analogy construction, helps them to make predictions about a new problem, or to put it differently, they can be used, if you like, to reveal students' beliefs, their ideas, underlying the way they make predictions, and explain, if you like, phenomena. Perhaps, although it's a little self-explanatory, I would say, it's worth it to define what I mean by student self-generated analogy, and how that actually differs to other analogies. So, as student-generated analogy, we can speak about spontaneously generated analogies and non-spontaneously generated analogies. So a spontaneous self-generated analogy is an analogy which is self-initiated. The analogy is generated by the student without any provocation. Of course, if you like, the student can still generate an analogy, but actually being prompted, being asked actually to do so. So our research actually has focused on the use of spontaneous analogies, for which actually we will see some examples from our study. Right, so just a little bit about the background, if you like, of the study, which I can explain more, if you like, and answer questions at the end, or as I said, we have reported on that study in a number of publications. So we have been doing research, if you like, cross-age research with students ranging from 10 to 17 years of age, and we asked them to make predictions in what we term, if you like, as novel situations that they have not themselves considered before, or at least they haven't considered them in the way they were presented to them. So they were asked actually to explain their predictions, more or less in terms of make a prediction, then explain actually what led them to that prediction, why they believe, if you like, essentially that this is the right prediction they made. Here we see one of these novel situations that ask students about weight and gravity. Perhaps a little bit conscious of time. I usually collect, if you like, responses from the audience when I'm presenting, if you like, part of our work, and I do that just to show how common our way of reasoning is, or perhaps how common our analytical reasoning is. Yeah, I've got a few more examples. If we have, if you like, times at the end, we can try, if you like, ourselves, if you like, in some of those. So that's an answer, if you like, from one of the participants, which actually typifies the answer we got, if you like, regarding this novel situation. So the student said, I'm not sure you had time. Do you have time to read the question?
Yeah, go for it. Yeah.
The student answered that, I think this is like when you have a ball and a feather. I've seen a ball falling faster on the ground than a feather, faster than the box with the elephant. In it will fall faster since the weight in it is greater, and there's a greater force in that box than in the other one. The heavier always goes faster, as in the case with the feather and the ball. So the student thought of that, if you like, situation, this novel situation, are similar to a ball and a feather. One box set, if you like, has an elephant in it. I'm not sure you can see that, and the other has an ant, if you like, in it. Difference in the weight, the heavier actually goes faster. Now, this response, if you like, exemplifies how, if you like, the Eureka prior knowledge, which is mostly experientially grounded, influence the understanding of the novel situation, as well as, if you like, the analogy that generated to approach it and make their predictions. So for this student, expectedly, we can argue the target situation was similar to a feather and ball, falling from the same height and used to reach a prediction or conclusion, if you like, for these actually problems that we're presented with. Now, with what such a reasoning does is that it leads, if you like, student to an incorrect prediction here, or the expression, if you like, of an erroneous idea, or better say, if you like, a scientifically incompatible idea. And this is, think about it, it's a common idea of having faster, or having actually, folding faster. More, if you like, is more of X, more Y. Now, the analogical reasoning here reveals that the idea comes from, or if you like, it's based on everyday phenomena and students' observation of those, which of course, as research, if you like, in science education shows, experience, if you like, is not the best teacher. Well, it's not always the best teacher, and does frequently, if you like, people and students to forming misconceptions. In this sense, the didactic, if you like, function of analogies can be extended from those that teachers generate and use to those that students generate, and the students' self-generated analogies, spontaneously or non-spontaneously generated, can serve, if you like, as a diagnostic form of assessment, revealing both the misconception that students might hold, but also, if you like, the prior knowledge upon which these are founded. So that's, if you like, the didactic use of analogies with reference to the student-generated analogies. Another interesting, I would argue, finding from our research is the heuristic, if you like, use of analogies in some of the prediction making and students reasoning. What we found, and the example I gave you, it typifies, if you like, that, exemplifies that, is that student-generated analogies frequently led them, if you like, to erroneous predictions. Predictions, if you like, incompatible with what will be the correct one, the scientifically accepted one. But we've also found that there are actually some analogical reasoning and some analogies that have the potential to lead to scientifically compatible predictions and scientifically, if you like, compatible understanding of those novel situations. And we shall see, if you like, some examples of these. Now, here's another, if you like, example. It simply asks what happens if the level of water in a glass with an ice cube when the ice cube melts. Again, perhaps I'll move on, and if we got time, I think I have, if you like, other novel situations we can go through. But the scientific, if you like, acceptable answer here is that the water level remains the same when the ice cube melts, and of course we will need Archimedes' principle of buoyancy, to prove this here. But just in a nutshell, a floating object, the ice cube in this case, displaces an amount of water equal to its own mass. Now, since by turning from ice, if you like, from solid to liquid, theoretically, the mass of water does not change. It will keep actually displacing the same amount of water. So the right answer, if you like, here, we were not looking for right answers, if you like, in our research. We were looking about the reasoning about making a prediction and telling us why actually they made a prediction. But what would we consider, if you like, as the correct answer, the scientifically accepted answer, is that the level actually remains the same. As I said, most of the students, as you can imagine, went for option A, ROA. The level, if you like, increases. But here we read one of the students' predictions and explanations. And the student said answer B, because if the ice cube, which is already in the water, is removed, the level will drop. And if we put it back, it will go back to level B. Therefore, it will melt, the level will remain the same. He further explains, that the water from the ice replaces the volume held in the glass of water. It is like the case in which space is left when we use a scoop to take out an amount of sugar from the sugar base. Where this amount is taken out, the space is refilled, and the level of the sugar in the base decreases. But in this case, we don't take out the ice cube or the water coming from it. It melts, but the water refills the space. So, is it close, if you like, to the scientifically, if you like, acceptable explanation? Yes, it is, because when compared, if you like, to other students' responses, the student actually here, by drawing on that analogy of taking, if you like, a scoop of sugar out of sugar base, it has, if you like, that idea, helps them actually build on that idea of refilling empty spaces, which other students actually didn't do. And the student actually reads a correct, as I said, scientifically acceptable explanation. And here's another one. That's perhaps some of you may be familiar with it. That's an example, if you like, discussing the dialogues of Galileo with his students, and he was having, if you like, those dialogues to explain how motion differs depending upon the reference frame. The ship is moving actually as you look at your screen to the left. The cannonball fires the ball. Which of the three persons is more likely to catch the ball? Most of the students predicted that person C, the back of the board, will catch the ball, and they explained that the ball actually drops straight down. Now, in doing so, it falls directly to the point where the cannon releases it without taking into consideration the velocity that the ball possesses, which is actually the velocity that the cannon and the ball actually also possesses. So for them, as the ball continues moving, the ball is going to land behind the cannon, and of course, they've used many different analogies, if you like, which, as I said, these analogies led them to to an incorrect, if you like, prediction. So the thing about, if you like, of a directly straight down motion than a parabolic one. But in terms of an heuristic, if you like, use of analogy in that case, let us look at the prediction and explanation of the student. So the student said, I asked that the person B is more likely to cut the cannonball. I believe that as long as the ball continues moving at the same speed, the cannonball does the same. And this is why it falls at the same point from which it was fired. It is the same with being in a bus, and we toss a pen in the air. It lands in the same spot, in our arms. So, if you like, from our point of view, previous research on the use of analogies, science teaching, and analogical reasoning pay only limited to no attention, I would argue, to the creative aspect of students' analogical reasoning in helping them to develop correct, scientifically compatible understanding. So in this sense, that's the origin of the word heuristic, heuristic, I discover, find, denotes. An heuristic use of analogy enables students to creatively use a familiar situation to generate expectations with respect to the outcome that can be transferred from the base to the target, thus facilitating, if you like, the understanding of an unfamiliar, of a novel situation in our case, unfamiliar concepts, phenomena, and so on. So we would first argue that analogies and their use could be, on the one hand, if you like, extended to provide science educators with a diagnostic form of assessment, as we said, that can help, revealing misconceptions, and also, if you like, the sources of these, where these misconceptions are coming from. But on the other, actually, the student-generated analogies, that heuristic, if you like, use of student-generated analogies can help for the identification of knowledge sources that can be productively used in the teaching process. And perhaps that's where we are now with regards to our research. The assumption that I would argue we reasonably make is that those heuristic user-generated analogies, because they're drawn from knowledge and base situations of the students, it may be the case that other students may actually be more likely to be familiar with those, if you like, analogous cases, or perhaps, if you like, those cases, if you like, those analogous cases generated by the students themselves, could more smoothly, if you like, harmonize with other students' repertoire of experiential knowledge than that of their teachers, and perhaps that's, if you like, open to research, if you like. They may be more effective, if you like, than those other teachers generate. So I think that's that's pretty much everything. So thanks for listening, and I'm happy to take any questions.